Okay, so I just posted some slides yesterday on the trunk class. Okay, so there are some materials that you need to know how to implement the portfolio calculation or computation in algorithms. So basically, in the following lectures, I will introduce some basic codings in R. And of course, just like you saw in the textbook, we have some examples in Excel. But to be honest, Excel is not really a good tool to help you to do a lot of data analysis and data calculation. So what I'm planning to do is will give you some homework requiring you to use the R codings. Of course, if you prefer to use Python, that will be fine, okay? Because both language can be implemented easily. And right now we have a lot of tools on the internet. So if you have any questions or problems, you can refer or check the internet for help. So I don't think this is a big problem. But the most important thing is that you have to implement some examples to help you to get a clearer picture of the portfolio analysis. So usually we will start from the most basic one. A minute. Need to open the camera. Okay. Okay, that would be better. Okay, so what I mean is that you have to understand the whole structure of the portfolio theory. So we have started. We started from the most basic one. So let's start from this slides first. Let me open this. Okay, I just made some modification to the slides, but anyway, there are a few materials on the internet. I think you can reference these materials by yourself. Some of the materials, some of the slides are based on these materials provided by some faculties in other universities. For example, like the most original lecture was provided by the Eric Zivat during that time. I think it's about in 2015. He was the faculty of Washington University in USA. I saw his lectures and I found his lectures very interesting. So I just include his lectures in my reference. So I think if you have time, and if I don't know if these websites are still available or not, but maybe you can check it out. But basically, this is very interesting. These materials are very interesting anyway. Okay, I just like to review what you have learned in the last 2 weeks. Basically, we have a portfolio, but you know, we won't mention a lot about the portfolio in linear algebra or in matrix algebra, but I must say that this is very helpful for us to handle some computation in coding. So I think this is also required, but don't be afraid of these terms or equations. If you really can't understand these equations, you can just focus on the implications of the equation. Okay, so this is the basic one. Because in the following lectures, maybe next week, we will cover more complicated models. Okay, so we start from the three asset cases. We have XA, XB, and XC. Okay, basically we have three assets, A, B, and C. We also have this X is for weight. Okay, which means we have to allocate our assets among these three assets. So this is weight, and the sum of the weights should be equal to 1, and the portfolio returns are weighted average of the individual asset returns. Okay, so this is quite straightforward. So if we start from the matrix algebra, then we have the returns. Okay, and this is the return. This is the average return. Okay, we have capital R, we have mu, we also have capital 1. So this is one vector. And X denotes the weightings for A, B, C, three assets. And sigma denotes the covariance of three assets. Okay, so usually we will start from the three asset case. But in the textbook, you might see two asset cases. Okay, but two asset case is too simple, and we will cover that also in the future, in the next lecture. But here, I just like you to become more familiar with three assets here. Okay, so this is the starting point, and then we can calculate the portfolio return. But usually, when you see these notes, sometimes you might be confused with the rate of return on assets, because here we have mu A, B, and C. That denotes the expected return, but usually in reality we will calculate the realized average return. Okay, so in other words, if we like to calculate the covariance matrix, for example, covariance matrix, we will use the historical data. Just like what you have learned in statistics, we use historical data to calculate covariance matrix. Okay. Okay, so this is the starting point, and then we can move on to calculate the portfolio expected return. And then this is very straightforward. And then we can also calculate the portfolio variance. So when we talk about the portfolio variance, we just use this equation. This is the weighting for three assets, and sigma denotes the covariance matrix. Okay, so we can calculate the covariance matrix, calculate the portfolio variance. But this is very straightforward. If you're really confused with the equation, you can just use two assets, okay, to do the calculation. If you are familiar with two assets, if you know how to calculate two asset portfolio variance, then you can extend from two assets to three assets. So this is the case for three assets. And then we can derive the portfolio distribution. So this is the expected return of the portfolio return and variance the portfolio. Okay, so usually we will assume the portfolio return following a normal distribution. But to be honest, this is not very realistic, because in the real trading world, we don't really have a normal distributed return. Okay, but usually we will start from the most theoretical one. Okay, and then we have this case. Okay, and then For example, if we have two portfolio case, okay, so this is a two portfolio. So similarly, if we have two portfolio, then you can also calculate the portfolio returns for each portfolio and also the covariance between two portfolios. So this is very similar to two asset cases. You can just treat the portfolio as one asset. Okay, so this is that difficult. So right now you can see the covariance of two portfolios here. We can denote the covariance of RPX and RPY here. Okay, to be the X plan sigma Y or Y plan sigma X. Okay, so this is about the covariance between two portfolio returns. And then so now let's come back to the portfolio, okay? If we like to, okay, so this is a very simple equation for the derivative of simple metric function, because we will use this equation later in our optimization process. So this is about the derivative with respect to vector. Okay, so we are talking about derivatives of simple metrics. But if you don't understand how this is going here, okay, going around here, don't be afraid. This, you can treat this just as an equation, a way to help you to do the calculation more easily. Okay, you can just treat this equation as a tool to help you to do the calculation in matrix algebra. Okay. So in the following, we can have this is just example about the matrix derivatives. Okay. So we can skip this. But now, coming back to the portfolio algorithm, the most standard problem is to compute the minimum variance portfolio, or we call global minimum variance portfolio. So usually we would have to know how to do this, how to find the answer or to the solution to the global minimum variance portfolio. So now the problem is, okay, we have to minimize the portfolio variance. Okay, so you can see we have an equation like this. We have an objective function. Remember what you have learned in your calculus in your first year in university. We have an objective function. We have to maximize or minimize the objective function, but we have some constraints, right? Which means we have an objective function subject to specific constraints. So this is very similar. In this case, we have an objective function here. We need to find the minimum variance portfolio. But the constraint now is the sum of the weights will be equal to 1. So this is our objective function here, sigma p square m equals to m plan, and you can just treat the m as a weighting, very similar to the x. Okay, in the previous slides, xa, xb, and xc. So don't get yourself confused with the notation, because when I prepare these slides, I don't have enough time to rewrite the equation. Okay, so you just use n. Okay, but in this case, we have m plan sigma n, and st means subject to m plan 1 equal to 1. Okay. Okay, so based on this, then we can set up the Lagrangian function. Lagrangian function, we have a lambda, so we said L function of n lambda. Okay, so this is the objective function plus lambda times m plus 1 minus 1. So this is a very standard Lagrangian function, and then we can calculate the first derivative with respect to weight, which is n in this case. So we call this as a first order condition. Okay, first order condition. I think that probably will refresh your memory what you have learned in your calculus course. But don't be afraid. Here we just restructure the equation using the matrix because we need to load up large data. Okay, we need to load up large data. We are not just talking about the one variable. We're just talking about the large amount of data. So in the future, if you are more interested in data analysis, you should be very comfortable with using the matrix algebra because that can save you a lot of time in deriving the equation. But anyway, we just following the slides here, okay, and we can derive the first order condition, and finally you can see down below here, okay, so this is the first order condition result. Okay, we just represent the result, okay, in matrix formula. Okay, and finally we can just represent the first order condition here. In this way we can call this as an times Zn equals to B. Okay, so An denotes the this matrix on the left hand side. We have 2 sigma 1 plus 0. We also have a Zn. Okay, we also have a B. Okay, so based on this formula, then we can derive the solution to this optimization problem. Okay, so finally we can find the answer to the minimum variance portfolio. So what we are looking for is what will be the optimal weight for us to construct the minimum variance portfolio. So we call this as a global minimum variance portfolio, or we call it as a GMVP. Okay, we usually have an MVP in the game player, okay, most variable player, but not in this case. This is called minimum variance portfolio. So this is what we are looking for. But there are so many, because there are so many minimum variance portfolio. What exactly we are referring to is the global minimum variance portfolio. Okay, in other words, we can plug in many different combinations of different weightings for assets, but what in this case we are looking for the minimum variance portfolio globally. Okay, so this is a global, and this is there's only one solution to this question. So the final solution to for Zn here is Zn equals to An inverse. So we call this as the inverse matrix times, okay, multiplied by B. So we usually call this as a closed form formula. So whenever you have a question, for example, I probably will ask you to find the GMVP, okay, for this portfolio. Maybe you will see these similar questions in your midterm exam. Okay, I'm asking you to find the global minimum variance portfolio weighting. Then you can use this formula. Okay, just plug in the formula and you get the answer. Okay, and based on this weighting, we can also calculate the portfolio returns. Okay, we can calculate the portfolio returns, but in this case, you can just use the historical average returns to calculate the portfolio returns. We haven't talked about the realized returns, okay, because that will be more complicated, but we will talk about that in the future. That involves a back testing process. Okay, so here we can just calculate the portfolio expected return mu PM. That will be equal to m plan times mu, and variance sigma p square equals to m plan sigma n. Okay, so this is very easy and not that difficult. And the of course, there's another way to find the minimum variance portfolio weighting. Okay, we can also use this approach. So we call this as an alternative derivation of GMVP. Okay, you can also follow this approach. So I'm gonna skip it here. It's not that difficult. So finally, after the derivation, you can find the closed form for this M. So this is another way to do to calculate the minimum global minimum variance portfolio weighting. Because in this way we just find the solution to lambda and we plug in the lambda and finally we get the N. Okay, so these two approaches basically are the same, but to be more clear, okay, about the weighting formula. So this is a weighting formula. You can use this formula directly to do the calculation. Okay. Okay. So this is about the GMVP. And then we have another problem because we just talked about the GMVP. That's the only portfolio that has the minimum variance portfolio globally. But in fact, we can also generate many minimum variance portfolios for a given rate of return. So for example, here we are talking about the Markowitz efficient portfolio. So you can see we have problem 1 and problem 2. Basically, they're the same. Okay, what we are looking for is to find the efficient portfolio that has the minimum variance or minimum risk for a given rate of return. So now we have one more condition or constraints. Okay, see, we have in our global GMVP, we only have one condition, which is sum of weighting is equal to 1. But now we add another condition. We have a target risk or target return. Okay, for the convenience of optimization process, we usually will handle problem 2. Okay, so problem 2 is to find the portfolio X that has the smallest risk measured by the portfolio variance that achieves a target expected return. So now we just restructure our problem. Basically, it's very similar to the GMVP, but now we only have one extra condition, which is mu px equals to x plus mu equals to mu p0. So this is a given target return. Okay, so now we have two conditions. So if you're familiar with the optimization process, this is not that difficult just because we just add one more condition. Okay, because we have a target, we have a objective function that will be minimized, but now we have to include two more conditions or constraints. So you can see here we can rewrite the Lagrangian function associated with problem 2 here. So now you can see we have a L function of x and the lambda 1, lambda 2, and lambda 1 refers to the first condition, lambda 2 refers to the second condition. So now we are doing the same thing. We try to find the first order condition and taking the derivatives with respect to our variable x, lambda 1 and lambda 2. Okay, so this is very similar to the GMVP. So based on these results, we can also derive the results in this way. So we can represent the first order condition in matrix notation here. So now what you saw here, what you see here is very similar to the GMVP. The only difference is that the the matrix content is a little bit different. We just added some more vectors here. Okay, but don't be afraid of this. This is not that difficult. You can just treat this as an equation. So I'm not asking you to be familiar with the optimization process, because everything can be done in codings. Okay, so we will just use codings to help us to implement the calculation here. But I must say that you have to know the theoretical issues involved in this optimization process, because codings is just a tool to help us to do the calculation or do the computation more easily. But if you happen to have problems in your codings or in your computation in the codings, then you have to go back to the theory, okay, and to see what really happened, what's the problem, what's wrong with the codings, because maybe the coding is just not about the coding itself, it's about the theory or formulas you created, okay, behind the codings. So I must say you still have to build up some basic knowledge about the matrix algebra here. Okay, so this is about the matrix. Okay, in other words, when you try to generate the codings, you still have to make sure that is the dimension of the matrix consistent with each other, so that I can do some multiplication, division, etc. Because if there is something wrong with the codings, it will generate error message. So that I can fix the error message. I can fix the problems or bug from the codings. Okay, so this is just for your reference. So finally, we can just generate the ZX. Okay, so you can see this formula is very similar to the one in GMVP. Okay, we also have an A matrix inverse multiplied by B0. Okay, so the formula is the same, nothing special. Okay, even if we can include more formulas, okay, we can do that as well. Okay, so here are some codings for your reference, because I just use a data called ferndata3.xts. But I have uploaded the data to the Tron class, so that you can also download the data. Here we have okay, so this is data for implementation of GMVP, MVP, and the Fission Frontier. So I'm using the data 3 Fern example data 1. Okay, so now you maybe you can try to download this data and implement the examples we mentioned in lecture. But we have two types of data. One is .csv, another one is .excel file. Okay, you can download either one of these and try to import the data into your R, and then you can do the calculation. Okay, but what I mean is that I'm using the same data as the data on Tron class. So I call this as a ferndata3.xts, but don't worry about the xts, because I just do some changes. I convert the data into time series data set. Okay, so don't worry about that. I just need you to focus on this. Okay, now what we are doing here, okay, is to calculate the minimum variance portfolio. Okay, so I just create a function. Okay, so you don't really need to create a function. You can just focus on the inner part here. I create the AX matrix. I also create a B0. Okay, So based on this, and then I can use the solve function. So what I'm doing here is AX matrix refers to the matrix we will generate. So here you can see AX equals to 2 times covariance return, and followed by the column means the return. So remember, just a minute, I will have to download the data and give you an idea about this. Okay, now you can see this is the raw data. Okay, raw data here. Raw data here, we have 3 company returns, Nordstrom, Starbucks, and Microsoft, and the date starts from 1995 March until 2000 January. So this is a monthly return. So this is monthly returns because we have a time series data. But don't worry, we only care about the data here. Okay, so this is a monthly return. So you have to import data to your R and do some calculation. And what we are doing here is to construct the AX inverse. So what is AX exactly about? Remember, in this case, we try to find the minimum variance for given return. So in this case, we have a given return which is mu equal to 0.005. Okay, so this is a given return. So we have to calculate the optimal weights for this given return, and finally we can find the weight. So here we have AX, and then we also have B0. So AX, what is AX? We have 2 sigma, mu, and 1. Okay, so so the first line here is to the R combined means row, right? Row combined. So we have 2 sigma, and the column means return, and the 1. Okay, so that is about the first one here, I think. Yeah, this is about the first one here. So that will be the 2 sigma will be 3 by 3 matrix. Okay, and the mu will be 1 by 3, but here we are using the row combine, so you can try yourself by yourself. Okay, and so that what we are trying to generate is the result of the AX. So we have we try to generate the AX matrix here. Okay, and then we can also generate the B0. Okay, so B0 is this vector. Okay, we can call this as a column vector. So based on this, then we can use solve function. Okay, solve function is to just will convert the AX into inverse of AX matrix multiplied by B0. So this is just a few lines of coding to help us to do the calculation. And finally, we can calculate the weight, and we'll get the finally we'll get the results. Okay, so this is just for your reference because codings can help us to save some time in the calculation. So I think that this is the most convenient way to do the calculation here. And finally, we can get the weight here. Okay, so finally you can see the weight for Nordstrom is 0.87. The weight for Starbucks is 0.11. The weight for Microsoft is 0.0075. Okay, and finally you get 2 more values here. So what is this? Does anyone know that? No. Okay. Actually, it's not that important right now, but I just like you to know, well, because we have two parameters here, lambda 1 and lambda 2. So these two values are referring to lambda 1 and lambda 2 here. Okay, because we are finding the solution, Zx. So what is Zx about? What is Zx about? Zx, the first 3 by 1 data is for weightings for 3 assets, right? And then the fourth element and the fifth element are referring to lambda 1 and lambda 2. So you can see we have 1, 2, 3. So this is X for 3, the weights for 3 assets. And the last 2 element is for lambda 1 and lambda 2. Okay, but don't worry, we are not interested, since we are not interested in these 2 values right now. So just forget it. We only care about the weighting. Okay, so this is a very simple example for you to follow in the future if you like to find the variance, minimum variance portfolio for a given return. Okay, so the following slides provides you a more detailed insight about what we are doing using the Lagrangian function. But this is not required. Okay, this is just for your reference, because maybe in the future you will have a chance to use this formula to help you, because we have the same problem. Okay, we have the same problem. We just restructure the problem. Okay, in this slides. So we also generate the Lagrangian function. But maybe you have noticed that we have you see the Lagrangian function is use negative lambda. Okay, and this is the first constraint or first condition, and use gamma. But basically this is the same as we use lambda 1, lambda 2, but now he's using negative. So I just add a note here. You can also define lambda as the following without affecting the results. You can also use the lambda plus lambda and plus gamma. It doesn't affect your results. Okay, so don't worry. But if you want to go into more details about the process, you can follow the slides here. We just take the first partial derivatives of Lagrangian function on W. Okay, W is X, what we are doing before. So after these derivations, okay, complicated derivation, finally we'll get the results. Okay, so I'm gonna skip this. Okay, I'm gonna skip this because this is just for your reference. Okay, finally we'll get the answer. Okay, so this is the final solution. Okay, so because this is just for reference, so I don't think it's very important to you right now. But I just need you to know, okay, we go through this complicated process of mathematical derivation. Finally, we'll get the results like this. Okay, so but finally, we still have another problem about how to construct efficient frontier. Okay, so we'll talk about this later. Okay, but we can just take a break right now.